Okay, so now what we're going to do is work on the basics for confirmatory factor analyses. So we're getting into how to go from EFA to CFA. So for this particular lecture, you should be reading the Buchanan chapter 3, and then I think that's it. Yes. So for the next section on second order models, you'll read some other chapters. Okay, so this is going to be a big section of the class where we're going to cover lots of different CFA types. Right. Another thing that is you can read is Klein's chapter 9. It's a really good reference chapter, but it takes the CFA sections that we're going to break into 3 or 4 parts into one giant chapter. So with the understanding that if you're reading that chapter, it's going to cover some things that we haven't gotten to quite yet, like fully structural models, and then second order models. And you're supposed to read that one for the next section anyway, so you might as well get started. And so I liked this picture that was at the front of the Buchanan chapter that really covers how everything is related in statistics, at least mathematically. Generally, most people start here at the ANOVA and t-test area, where you're trying to just figure out how to work with categorical IVs, continuous DVs, or continuous IVs, continuous DVs. But all of that really fits under regression. So ANOVA and t-test are just a special type of regression where you have categorical IVs, although in multiple regression it's much more flexible because you don't have to have categorical IVs. And so all of that really falls under like linear models or least squares types of models. What we did in the last section with path really was multiple regressions. We did one very simple 3 variables predicting y, and then we did an example of mediation, so all that fits under path. We're hopping over here to CFA. So confirmatory factor analysis is the first type of model we're going to use with a latent variable. So we're going to create latents today. Underneath that falls EFA, because EFA is where a special type of CFA. It's more flexible CFA, actually. And item response theory, which we won't get till the very end of the semester. And item response theory is where the DV is actually categorical, or at least treated categorically, as opposed to, the measured variables are treated categorically, as opposed to continuously, which is what we do with EFA and CFA. Another type is the traditional multivariate, so these are your fully latent models, and then technically canonical correlation counts under here. So CanCor, the way that works, kind of sounds like a dance at first, is that it's a correlation with lots of IVs on one side and lots of DVs on the other. And so really it's actually a special type of CFA sometimes, but people treat it kind of separately because it is run in much different fashion than CFA. The focus is different, although mathematically they might be very similar. Okay. And all of that fits under the umbrella of SIM. So unbeknownst to you, technically in the theory you've already been doing some SIM, it's just we don't run it in the same complicated way. We tend to focus more on degrees of freedom being about participants over here, because we saw in path why that might be a better idea. Whereas now we're really working on degrees of freedom being parameters instead of people. So with CFA models, you generally, and I'm going to approach this from a very basic scale development sort of approach because that's my specialty. So with an EFA, you'll have a bunch of the questions or items, and sometimes you have an idea of how many factors to expect, sometimes you don't, and you just sort of let the questions go wherever they want. And so you're kind of throwing everything at the wall and seeing what sticks. And we're really hoping that the items go where they're supposed to go. That doesn't always happen. And so I have several models where the items did whatever they wanted, but not what I wanted. And then we'll slowly remove bad questions. So this is where we started this semester, just on a review of EFA, of taking out bad items until we got to a simple solution, where each item loaded on one and only one factor. And then we hoped for good model fit as well, with good reliabilities and a good interpretation. And so with that, we'll still have little loadings on the other factors, but we want them to be small. So we focus on the simple structure idea where the loadings on the factors, the other factors are small. But with CFA, we're actually going to set up that model where the questions go where we expect them to go and force the other loadings to be 0. So we take that simple solution from EFA and move over to CFA, where we say, okay, these 6 go here, these 6 go here, everything else, no loading. So we're effectively testing that EFA to, does this question actually go here? And is the cross-loading, or the loading for the other factors, effectively small? So did this simple solution replicate? Okay. So we're going to force those cross-loadings to be 0 by not defining them. We're going to see if that model fits. So this is you can think of it as confirming a CFA, so the confirmatory part of this. So I have a picture. So this is a very basic 2-factor CFA. Pretend like you see the little air bubbles out here. We're going to talk a lot about standardization in this lecture, about where that one can go and how we can use it in different ways. And then in the example video, we'll look at how to run the code both ways. But what I mean by setting the cross ones to 0 is effectively by not allowing an arrow to go from this bubble to this question, because this question is tied to this second one here. And so we're forcing these 3 to only go with this factor, and these 3 to only go with this factor, and not allowing the questions to load on more than one factor. There are times that you can do that. There are certainly theoretical ideas where they should load on both. And then when we work on bifactor models in the second order section, we'll actually do that on purpose. But in a very traditional sense, we don't let them load on more than one. And so each item separates out into its own factor. Okay? And then they'll each have their own little error out here. In CFA, we expect a correlation between the 2 bubbles, but I'm not going to get too far ahead of myself. That's on the next slide. Okay, or one of the next slides. Brief talk about reflexive and formative direction arrows, and then we won't come back to this until we get to the fully structural part, but we will work on this again. The most common thing is this reflexive or reflective technique, where we think the latent variable causes the manifest scores. So this one is X, and it causes the output on Y. So this is where I really started when we started talking about IQ, which is actually the example for today. My IQ causes my answers on the whisk, not the whisk creates IQ in my head. Okay. So the latent variable causes the manifest variables, or the measured variables. And so the purpose is to really focus on the relationship between measured variables as explained by this factor. And that's conceptually the same as EFA. That's how we treat it in psychology, is that these latent variables cause these question outputs. So this undefined phenomenon is actually why we're seeing the output we're seeing. Formative indicators, though, the arrows go the other way. And so the latent variables are a result of these manifest variables. So if you can see, the little arrowheads are going into the latent variable here, and it would have an error. Okay. And that's more similar to PCA, where we're getting this pattern of data because of the questions or the items. Theoretically, this isn't something that I do very often anyway, but I have seen it used in a demographics sort of way. So you can create a demographics profile of people, but you didn't cause their demographics. So you can say age, socioeconomic status, gender, and ethnicity create this demographic profile of someone, versus thinking of it the other way. And that to me is one of the best types of formative indicators, is a profile that you're trying to build based on these variables, versus saying that this latent variable causes these outputs that you see. So we won't use formative too often. We'll talk about those a little more in the fully structural model, on how to create them, because this is a little different. Okay, so the manifest variables, or the measured variables in CFA, are sometimes called indicator variables, as if they don't have enough names. They're manifest or indicators, they're measured. But that idea is based on the theoretical component of that they indicate what the latent variable is measuring, since we don't actually directly have a measure of the latent variable. So I can't really like pop an IQ out of somebody's head. Instead, I am using these scales to indicate what we expect their IQ to be. Okay, so some general rules about CFA. So latents will be correlated. Remember that Lavon does that for you automatically, as we saw in some of the last examples where it did it and we didn't necessarily want it. Okay. The reason that we allow that is because that is similar to an oblique rotation in EFA, and we don't really expect too often to have uncorrelated latent variables, otherwise why are they on the same scale? Okay. Each factor section has to be identified, so we're going to include scaling in each section in one way or another. We'll get to different ways to do that in a second. The arrows are reflexive or reflective. I've seen it both ways, and I learned it, I think, as reflexive, so that's why I keep typing it this way, but I think in the book it talks about them as reflective. Same idea. Because we think that the latent variable causes the measured answers, and you'll have error terms on each of your measured variables. Okay? So some of this isn't new, some of it is this each factor section part is new. And what I mean by that is that each piece has to have, each latent has to have a scale. Okay. So in general, we're going to leave our error terms uncorrelated, but we can actually correlate them, and we'll have some examples where we do that. So in theory, these questions all measure the same factor if they're together, lumped together on the same factor. So their answers are going to be correlated because it's the same person that's taking them. So often in your modification indices, or the things that we can use to see maybe where our model isn't working correctly, you'll see that it wants to correlate some of the errors. And sometimes that's a good idea. And if you look at the questions or the items, you'll be like, oh, well, duh. If I look at these two questions, they're basically the same thing. And because they're basically the same thing, probably I should get rid of one of them, but I can correlate the errors between the two as well. Okay. So you generally have to have kind of a good story for that, or a good theoretical reason, and the way you'll notice them is strong modification indices. And we're going to look at some of those in the example, so we'll see better what those represent and how they work. And this is how it might look. I drew some little error bubbles on here, but what you'll see on the output is an extra covariance arrow out in SimPath, out here on the ends. So you'll get the little double-headed arrow on the question or the item, because that's how it draws the error variances for you, but then it'll draw you another little covariance between these two. So with CFA models, we want to look at the factor loadings, or the regression coefficients. It's the same idea as EFA. You want the relationship between each item and its latent variable to be really strong, because otherwise why are you using that question? And what we'll do is we'll be able to look at the unstandardized loadings, and that will be in the scale of the data. But then we can also look at the standardized loadings that are more similar to the output you look at in EFA, so it's easier to interpret. And so this actually does not pop up in the output for Lavon so much as it does in output for other programs. But if you're looking at sometimes what are called pattern coefficients, versus structure coefficients, pattern coefficients are similar to unstandardized coefficients, so the regression coefficient. And so it's basically how much does each manifest variable increase for each unit of the latent variable. So if I increase on an IQ, how many points should I see on each of the subscales of the whisk? And remember, it goes in that direction. So how much does the latent increase? How much for each point of the latent do you get on the manifest? Because of the direction of the arrows. So the latent variable is technically x. So for every 1 unit increase in x, or latent, we get regression coefficient increases in y, or those manifest variables. And that's particularly important if you're using it in a predictive capacity. The structure coefficients, or I would say this is the completely standardized solution, is the correlation between the latent and the manifest variable, and that's more of a strength question. So which one is the strongest? Because pattern coefficients are in the scale of the data, and so if they're not all in the same scale, that'll be represented. But in a structure coefficient, it'll be totally standardized, so you can't compare them to each other. So it's kind of like B and beta. However, pattern and structure coefficients are the same when there's only one latent variable, but they're not equal when there are multiple latent variables. And this isn't going to affect you too much using Lavon, but if you're using some other programs, this will be important. All right, so let's say we've built our CFA model. Let's talk a little bit more about identification for CFA models particularly. When we did path models, we're really more concerned about not putting in so many parameters that we run out of degrees of freedom. With CFA models, often you have enough parameters, but you don't have enough parameters in each little section. Okay. So at best, a latent variable should have 4 indicators. Okay. So with 4 indicators, that means 4 different items or squares that go with it. Okay. If you don't have that, you can do 3 indicators and no error variances can covary. If you don't have 3 indicators, you can do 2. The error variances can't covary, and then you also have to set the loadings to be equal to each other. And that's just so that you get the whole thing identified. Now on this end, I've gotten away with not setting them equal to each other because it'll still run. But the more complicated your model is, the more difficult that becomes because you just don't have enough wiggle room, so to speak, to really make this work. So they have to have 2 indicators to even run, but 3 and 4 are better, and even more would be great. And you'll see this because it'll warn you that it's not identified and then it won't run. But so for identification, let's talk about scaling. So we're going to scale the latent variable, and scaling helps with identification by controlling the number of degrees of freedom. So really we've been using this 1 on those paths in these pictures. Go back here. So we've been using the 1 to indicate that this is where the scaling occurs, but that also controls degrees of freedom because these are not estimated. And what are my other options? Well, there's 3 in general. We can standardize the latent variable. So that's constraining our latent variable variance to 1, which essentially sets the whole thing to a z-score scale. It makes the double-headed arrows between latents a correlation. And you really, if you're going to do it this way, you're going to use the unstandardized solution. And then what you'll actually see is in the Lavon output, this unstandardized solution and the standardized solution are the same, because otherwise it would standardize this standardized solution, if that makes sense. But this will constrain all the variance on the latent side. And then all of the parameter estimates are going to be standardized, so in z-score formats. Now remember, z-scores can go over 1. This isn't completely standardized. This is just scaled to beta, basically. And so basically what you'll see on in a picture is that there'll be estimates for all the paths, and then out here with the double-headed arrows, the variance on these, you'll see a little 1. This will still be correlation, but this will be estimated at 1. Other thing you can do, and the more common way, is called a marker variable. And that sets one of the factor loadings to 1, and that's what we're really going to do most of the semester. And it gives those items a scale. And generally it's the scale of the data, because most of the items on the scale should be the same. But you could standardize that as well. So when you look at watch the example video, what you'll see is I'll talk about use the marker variable option, so here, but also ask for the standardized solution, and then you can look at both. And so you'll have both of them so that you can interpret it in the scale of the data, the unstandardized solution, with a marker variable, or you can look at it in a standardized way for z-scores, or you can look at the totally standardized solution. And so I like that one the best because it shows me all 3, versus when I set it to do this, I can only see 2 of them. So I like it better because more information is better than less information. And that'll make more sense once we do some examples. Another option is what's called effects coding. And that estimates all the loadings, but it constrains them to an average of 1 across latent variables. I don't know if that's super popular. Okay, all those options are going to give you different physical loadings, but the fit doesn't change. Because all you're doing is changing where the scaling occurs. You're not changing the way the covariance table is estimated. And so the model fit stays the same. So it doesn't matter if you scale on the latents or scale on the manifest variables, and it doesn't matter which manifest variable you scale on. Okay? You're going to get the same model fit. Now the loadings will change. So if you're interested in the p-values for each loading, what I tell you to do is scale it on one, switch it, and look at the other ones. And so a couple of little concerns at the end here is empirical under-identification. And so that's when you have a factor loading or an item loading that's very close to 0. So that question is no good. Or the factor correlations are very close to 1. And that implies that you're over-factoring. So you have too many factors. And so that is mathematically identified if you've scaled it correctly, but empirically under-identified because you have included items that shouldn't be included, or you've added more factors that shouldn't be included. So you've kind of given it more things to estimate when you really shouldn't be. And then what I tell you to do now is to go and watch the example video. And what's new in there is we're going to talk about how you can go from the correlation matrix to a covariance matrix. Because remember, if you only have the correlation matrix, it's always the standardized solution because correlations are standardized. So this will allow me to take my correlation matrix and enter it and be able to look at an unstandardized solution. If you have the covariance table or just straight raw data, you will be able to look at both unstandardized and standardized. But to do this function, you're going to need the correlation table and the standard deviations of the items themselves. But that's something that you actually might often find in research papers, is at least the means and standard deviations for each thing and the correlation table. So it's a way to estimate from summary data rather than the raw data if you're trying to replicate someone's model or create a model from someone's data that's already been published.